Hi guys, welcome back to my channel. Nice to see you all again. And in this video, we'll discuss the last subtopic in topic 1, which is your 1.6 basic reaction in organic compound. I split this subtopic into two parts, which is your part 1 and part 2. So today we are going to talk about part 1. And in part 1, we are going to talk about bond cleavage. We have two types of bond cleavage, and we are going to talk a bit about intermediate, what is actually free radical and carbocation, and also their stability. So let's start. Bond cleavage. What is actually bond cleavage? Bond cleavage is actually bond breaking. So we have two types of bond cleavage, homolytic and heterolytic. Homolytic cleavage over here is same. What needed to be the same in homolytic cleavage? And we have heterolytic cleavage. Heterolytic cleavage means different. What needed to be different in heterolytic cleavage? Let's see. Homolytic cleavage. Okay. Homolytic cleavage means that the covalent bond will break symmetrically, alright, between the bonding atom. The covalent bond will break equally between the bonding atom. I have a bonding atom of X and X. And everybody knows that in one bond, there is two electrons. So when the definition says covalent bond breaks symmetrically, means that the bond will break equally over here. One of the X will take one electron, another X will also take one electron. That is what we mean by symmetrically breaking. This bond breaking can only happen at the non-polar bond. That's why when I use an example, I use the example between X and X. Non-polar bond means same electronegativity. Alright, the electronegativity between the bonding atom must be the same. So you can see over here, you have your X and X, they have the same electronegativity. Another example, you can have Cl, Cl. You can have Br, Br. You can have your hydrogen with hydrogen. So the non-polar bond is normally when the bonding atom are the same normally. Okay, so that they can have the same electronegativity and the bond will break symmetrically. Okay, so that is the first requirement in your homolytic cleavage, non-polar bond. Next, free radical will be produced when this homolytic cleavage happens. What is actually free radical? Free radical is when you have your Cl holding an unpaired electron. When you have your Br holding an unpaired electron. One single electron without pairing. Okay? We know that electron always come in a pair. We always come across a structure like this. When you draw your Lewis dot symbol, you always draw them in a pair, right? So when the thing is in a single, they're only holding one, that is your free radical. So free radical is a species with one unpaired electron. And why free radical will be formed? Because this electron is taken by one bonding atom. This electron is taken by one bonding atom. So X is holding one electron now. X is holding one electron now. The one unpaired electron. The same thing over here. The electron taken by hydrogen. The electron taken by hydrogen. So the hydrogen will be free radical with one single unpaired electron. That is what we call free radical. Sunlight and UV is needed for this homolytic cleavage process because the function of sunlight is to provide energy for the homolytic cleavage. Alright, the sunlight is the energy, source of energy for this homolytic cleavage. Let's look at how the homolytic cleavage happens. Homolytic cleavage can happen with a condition that you have a non-polar bond. So I give you a very simple example. Br, Br that you use a lot in your bromine test. So what happened in this Br, Br is, in this one bond, you're actually having two electrons. Everybody know one bond holding two electrons. And when the bond breaks symmetrically, when the bond breaks equally, so one of the electrons will go to the left Br, one of the electron will go to the right Br. And if you look at the type of arrow that I'm using, the arrow that I'm using over here is a half-headed arrow. Okay, can you see the half-headed? The half-headed arrow represents one electron. Alright, if you're having a full-headed arrow, that represents two electrons. And over here, we only have one electron moving at one time. One electron move to the left, one electron move to the right. That's why you are using a half-headed arrow. Be careful with the arrows. Arrows are the things that giving you marks in mechanism. So make sure you know what type of arrow is used in your reaction. So over here, what is needed for this homolytic cleavage to happen? You need to have the presence of UV. If you don't have UV, you won't have energy for this homolytic cleavage. So you need the presence of UV for this homolytic cleavage. And what is being produced as a product? Product will be your Br free radical, Br with a single dot, and also another Br with a single dot. Make sure the single dot is obvious and significant. The position of the single dot can be in anywhere. It can be on the left, it can be on the right, on the top, it can be at the left, it can be at the bottom, it doesn't matter. But make sure the single dot is obvious and significant, okay? And that is how your homolytic cleavage happens, the bond breaking. The homolytic bond breaking over here is because this bond will be break equally. One to the left, one to the right, forming free radical with the presence of sunlight. Okay, that is homolytic cleavage. And homolytic cleavage can happen to anyone as long as they are non-polar bond, as long as they have a similar electronegativity. So other than Br, normally it can happen also to Cl. Okay, it will normally happen to Cl as well. So be careful with the arrow. The arrow that I will normally put, one is on the top, one is at the bottom. Okay, that is the normal way that I will draw it, because one electron will be moving to the left, another electron will be moving to the right. And for this reaction to happen, we need to have one condition. And the condition over here is UV. Make sure you have the presence of UV, because without UV, this homolytic cleavage will never ever happen. And the product produced will be the free radical of chlorine twice. You have two free radical of chlorine produced over here. So that is your homolytic cleavage, where the bond break equally in a non-polar bond. Alright, where the bonding atom have a similar electronegativity. That is your homolytic cleavage. Simple. Let's move to heterolytic cleavage. Heterolytic cleavage over here, where the covalent bond will break unsymmetrically. Okay, the covalent bond will break unsymmetrically. So when the bond break unsymmetrically, the bonding electrons will be transferred to the more electronegative bonding atom. The stronger electronegativity bonding atom will be able to attract electron towards it, because I have the higher ability of attracting electron. So both of the bonding electron, both mean two of the bonding electron will be moving to the more electronegative atom. Therefore, it will have a polar bond. Polar bond means different electronegativity. You must have someone that have higher electronegativity than another. Last but not least, you'll produce a cation and anion. Cation means positive charge ion and ion means negative charge ion. A very simple example that I can give to you before any further example is your HCl. Alright? And if you look at your HCl over here, I have two electrons in the bond. So what happened to two electrons in the bond? I have H, which is partially positive, Cl, which is partially negative, where Cl is having higher electronegativity than hydrogen. Chlorine have the ability to attract electron stronger than the hydrogen. So both of these electrons will be attracted to the chlorine. Look at the type of arrow I'm using. Okay, we'll talk about that further later on. And what are you producing? You'll be producing your cation H+, and also you'll be producing your Cl- anion. Because hydrogen loses the electron, that's why it becomes positive. Chlorine accepting the electron, that's why it becomes negative. So that is your cation and anion. And that is your heterolytic cleavage. Let's look at more example of heterolytic cleavage. I can have something like this. Okay, 3 carbon with 3 hydrogen and a Br. So everybody knows that In the bond, we have 2 electrons. So, C and Br, who is stronger electronegativity? Br is stronger in terms of electronegativity. Br can attract electron easier. So, both of the electrons will be moving towards Br. Okay, both of the electrons will be moving towards Br. And when both of the electron is moved towards Br, what happened to the carbon? The carbon will be losing electron. When the carbon lose electron, then it will become positive charge on the carbon. While the Br right now is accepting electron, therefore Br can become Br minus because I accept more electron from the bonding between carbon and Br. And that is your cation for the positive charge, and that is your anion for the negative charge. And before I proceed, look at the type of arrow that we can use. We can use full-headed and we can use half-headed. But in this heterolytic case, we must always use full-headed because we transfer 2 electrons at one time. So by that in mind, look at the arrow that I'm using. I'm transferring 2 electrons at one time. That's why one person become positive, another person become negative. Your cation and your anion will be formed in your heterolytic cleavage. So heterolytic cleavage will happen when your bond is a polar bond, where the bonding atom have different electronegativity. And obviously, the one with higher electronegativity will win, because higher electronegativity obviously is the one that having ability to attract more electron. See that? Simple. Another example that I can give to you, let's use some ring. Okay, another example that I can give to you is when you have OH. So we know that oxygen is more electronegative, and then you have a carbon between OH. So what happened in this compound is both of the electrons will be moving to the oxygen. So when both of the electrons move to oxygen, then the ring will become a positive cation on this particular carbon with the presence of OH minus as an anion. Okay? Again, look at my type of arrow. We are using full-headed arrow to transfer both of the electrons so that the carbon become positive, the OH minus become negative. Before I move on, let's look at this. We do not need the presence of sunlight. We do not need the presence of UV because this process can happen due to the different electronegativity. Because Br is always having higher ability to attract electron. Oxygen also higher in electronegativity means that oxygen always have the ability to attract more electron. So we don't need the presence of UV. We do not need any external energy for this process to happen. So I hope by now you understand what is your homolytic cleavage and heterolytic cleavage. Always remember, cleavage means breaking. Alright, heterolytic means break differently, homolytic means break equally. Okay. Next, we are going into types of intermediates. Okay. We have 3 types of intermediate. The first one, free radical. The second, we have carbocation. The third, we have carbanion. Free radical is an unpaired single electron. Okay, we have an unpaired single electron where you have like this. Carbon with 1 single electron, chlorine with 1 single electron, hydrogen with 1 single electron. That is your free radical. Carbocation. The carbo itself represents carbon and the cation represents positive charge. So carbocation is actually a carbon with positive charge. Carbanion, obviously carbon and anion. Alright, when you have anion means you're always holding a negative charge. Carbanion is your C minus. And in this video, we are only focused for free radical and carbocation. We are not looking into carbanion. So free radical, what is actually free radical? Free radical is an uncharged atom or molecule with an unpaired electron. The single electron that you're holding in Cl just now, in Br just now, in hydrogen just now, and so on. That is your free radical. Free radical will be formed from homolytic cleavage. Remember, homolytic cleavage just now is a non-polar bond. You need to have the presence of your non-polar bond, where the electronegativity between them are the same, like your Br. So the electronegativity between bromine are the same, so that the bond will break equally. Require the presence of sunlight, of course, because sunlight provides energy. Homolytic cleavage. Okay? We have a lot of different free radical, but the free radical that you will normally come across is your Cl and Br in the bromine test for Br, and also H+, and also free radical like the carbon. Alright, you might have a free radical on the carbon ring, you might have a free radical on a CH3, CH2 free radical. Okay, so that is all your free radical because you have a unpaired electron. So next, we move to carbocation. What is actually carbocation? Simple. It's actually a carbon with positive charge. Very simple. It will normally form from heterolytic cleavage, like just now when I showed to you, you have the presence of CH3 and also Br. So when the Br took both of the electron, then your CH3 will become a positive charged carbon that we call carbocation. It definitely requires a polar bond with different electronegativity. That's why I chose between carbon and Br, where Br having higher electronegativity. So when Br having higher electronegativity, Br will have the higher ability to attract electron to it. Okay, so that the carbon will be losing the electron and carbon become carbocation. So that is your free radical and carbocation. Next, let's look at stability between the free radical and also the carbocation. This is the conclusion of stability that I can give to you, where you can see over here that is all your free radical, okay, of the carbon. And then we have carbocation, so you have all the positive charge on your carbon. That is your carbocation. So what makes them more stable? If you remember the class of it, so this free radical right now is a tertiary free radical because this carbon is holding to 3 carbon. This one is a secondary free radical, primary free radical, and this is what we call methyl free radical, alright, because it's only holding 1 methyl group. So carbocation, same thing, that is your methyl, that is your primary, that is your secondary, that is your tertiary. In a conclusion, you can see that the stability is higher in tertiary compared to secondary, compared to primary, compared to methyl group. Okay, so that is the stability. The question over here is why tertiary is more stable. Alright, the conclusion is like that. Tertiary is more stable than secondary, more stable than primary, more stable than methyl group. But why? So in this, we are going to discuss why the stability works like that. Why the tertiary is more stable than the secondary and more stable than the primary and also the methyl group. Okay, so we are going to talk about the stability over here. Before the stability, I want you to focus on this R group. What is actually this R group? Okay, what do you know about this R group? R group over here is actually your alkyl group. What is actually alkyl group? Alkyl group is actually your carbon group. Alright? No matter it's a ring carbon, straight chain carbon, branches carbon, 1 carbon, 2 carbon, 20 carbon, as long as they are carbon group, they are what we call alkyl group. And we represent by using the symbol R. Okay? And this R group over here, they are actually electron donating group. Alright, they are actually electron donating group that we can use a symbol of EDG. So what is actually electron donating group and what is the function? Why, when I have a lot of R group, I am more stable? So before I proceed to the relationship between the R group, the electron donating group, and also the carbocation and the free radical, I want to remind you that the free radical and also the carbocation is those people that have not enough electron. So it become a free radical because you're only holding one electron. It become a carbocation positive charge over here because you are losing electron. You are losing electron, that's why you become positive charge. When you lose electron, you are also not having enough electron. Alright? So when you're not having enough electron, you need a group of people that will give you the electron, that will help you with your electron. Okay? So let's see. Let's try to use this tertiary carbocation. When I have a tertiary carbocation, means that the carbocation is holding R group. Why is a tertiary? Because all your R group is your carbon group. So all this is actually holding carbon, carbon, carbon. Okay, that's why it becomes tertiary. All this is your carbon. And why the tertiary carbocation is the most stable? Why is that the most stable? Because you have 3 electron donating group. This electron donating group will help you to disperse the positive charge. Disperse over here means that it will help you to minimize the carbon charge. Alright? It will help you to minimize the positive charge over here. So when the positive charge is minimum, is decreased, then the carbocation will be more stable. So imagine I am C positive. I have 3 friends. Alright, I have 3 R group that will help me to disperse my charge. My positive charge can be given to first R group, second R group, third R group. I have 3 persons to help me by taking my positive charge. Compared to a secondary, guys, a secondary carbocation is only having 2 R group. Alright? And the positive charge in your secondary carbocation will only disperse by 2 persons. So 3 persons helping you and 2 persons helping you. Which one is more stable? Of course, 3 persons. Alright, 3 persons is helping you to decrease the positive charge. Everybody take a bit. But over here in the secondary, you only have 2 persons helping you. And go to your primary, guys. Go to your primary. Your primary carbocation over here, alright, holding only 1 alkyl group. 1 alkyl group means 1 person only helping you with the positive charge. Your positive charge can only be dispersed, can only minimized by 1 person. Comparable, primary and tertiary. 3 people helping you and 1 person helping you. Which one is easier? Of course, 3 person is helping you. Is more stable. Alright? The same thing applies to all your free radical above. The tertiary will be more stable because you have 3 alkyl group. Alright? You have more alkyl group in your tertiary to help you to disperse the positive charge. That's why they become more stable. That's why you come to a conclusion where your tertiary is most stable compared to your secondary, compared to your primary, compared to your methyl group. Because your tertiary having 3 alkyl group that will help you to disperse the positive charge and minimize the positive charge. So the carbon holding positive charge will be more stable because the positive charge is shared between 3 friends. Alright? Easy? The complete sentence works something like this. The alkyl group are all electron donating groups. So we know that all this alkyl group is your electron donating group. It will help to disperse the positive charge on the carbocation and the free radical. Okay? It will help to disperse the charge on it. And this is what we call inductive effect. This process is what we call inductive effect. And inductive effect will increase when the number of alkyl group increase. Okay? Last but not least, the stability of the carbocation and the free radical will increase with the number of alkyl group. The higher the alkyl group, the stronger the inductive effect. The stronger the inductive effect, the more stable is the carbocation or the free radical. Simple? Alright, that is the stability where tertiary is more stable than secondary, more stable than primary, more stable than methyl group. So that's it for this part 1 video of your subtopic 1.6. Everything in this video is very simple but it's very new to you. So make sure you understand them very well, and if you don't understand, drop me question in the comment and I'll get back to you as soon as I can. And if you like this video or if this video able to help you, give me a like and don't forget to subscribe to my channel. I'll see you back in the next video and thank you for watching.